Okay, we are recording. So I know that not everybody attend, and I want this to be in the recording. So I was saying that all the homework are for 2 people. So we already created the groups, and you need to work with your partner. I was saying that if the homework have 4 exercises, you cannot say, okay, student A do exercise 1 and 2, and the other student B, do exercise 3 and 4. Okay, it's not the objective of doing groups. So you need to come here in the university, meet with your partner and do the homework together. So both of you learn of all the exercises, not the one that I'm doing, and I don't learn anything from the other one. That's not the idea. And of course, if you email me a question about the homework, be sure you copy to your partner, because you don't work alone. You work with your partner on that. So your partner needs to know what you are asking. So the partner also learn about what you are asking. Okay, so last time I think we did this exercise, the last one that we did. Let's do this one. This one is quite easy. What you can say about this one? We will have solution or we will not have solution? So we try to find an inverse for 17 modular 81, modulus 81. So we know that we will have a solution if and only if 17 and 81 are coprime. So 17 is a prime number. And inside 81, 17 is not there, no? 81 is 3 times something. We can ask here, we factor 81. So it's 3 times 3 times 3 times 3. So they are coprime. Since they are coprime, we do have a solution, no? I don't see my... Did I close it? Okay, I don't know. Okay, so it will be just to find the inverse of 17 modulus 81. This one is a little more complex because there is not congruent to 1. So let's try to do this one. So let me open Paint and copy the exercise. So we have x is congruent to 10 modulus 13. Okay, what can we do with that? Okay, so we may, for example, want to add 2x on both sides. So if I add 2x on the left side and on the right side, 11x plus 2x will be 13x. And here, if I add 2x, I will have 10 plus 2x, no? Modulus 13. So 13x is 0, modulus 13. So I can just replace, this is the same as 0, is congruent to 10 plus 2x, modulus 13. So here, the left side and the right side can be divided by 2. So I can do it. 0 divided by 2 will be 0. And if I divide this term by 2, it will be 5 plus x. Now, if I divide this by 2, I have also to make a modification here. I have to say that it will be congruent to 13 modulus the GCD of 13 and 2. So the greatest common divisor of 14 and 2 is 1. So this will be 1, 13 over 1. So at the end is the same thing. So I have the same as x is congruent to negative 5 modulus 13, isn't it? And negative 5 is the same as 8, no? Because I can add 13 here. So 13 minus 5 will be 8. So it's the same as 8 modulus 13. So at the end, I know that x can be, for example, it can be 8. 8 plus 13 will be 21. 21 plus 13 will be 34. 34 plus 13 will be, okay, blah, 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 no? 8 minus 13 will be negative 5. Negative 5 minus 13 will be negative 18. Okay, let's do one more value. Negative 18 minus 30 will be negative 31. So those are the possible solutions, no? According to what we did. So let's verify that with a small program that we have all these solutions. So I'm going to go back here, and we did have a program that we call in the desktop. I think it is called solution.py. So, okay, I want to go from negative 50 to 50, inclusive is okay. So I want to resolve 11 times x modulus 30 should be 10. Okay? 11 times x modulus 13. Modulus 13 should be 10. Okay, so this is correct. I'm going to execute that, and it show me the solutions that we have between negative 50 inclusive and 50 inclusive. So we can see the negative 31, we can see the negative 18, the negative 5, the 8, the 21, and the 34 that we did fine, no? So that's a method. There is another method. Let me show you another method to do that. So there is a theorem that says that if I have to resolve the following equation. A times x is congruent to b modulus n. So if A and n are co-prime, then it's exactly the same as resolving x is congruent to the inverse of A modulus n times b modulus n. So we can use this property. So to do so, first I need to see if 11 and 13 are co-prime. They do. 11 is a prime number and 13 is a prime number. So it just tells me that, okay, I can just solve this problem. X is congruent to the inverse of 11 modulus 13 times 10. I can just solve that. So I need to find who is the inverse of 11 modulus 13. So let's do it. For that, I'm going to express 13, in function of 11. So it's 11 times 1 plus 2. I don't have a plus 1 here. I have to keep going. So now I'm going to express 11 in function of 2. 11 is 2 times 5 plus 1. Another 1, I can stop. So I can say that 1 is 11 minus 2 times 5. So I already took advantage of this equality. Now I'm going to take advantage of the other one. And I'm going to replace these two here. So 1 will be 11 minus 2 is 13 minus 11. So 13 minus 11 times 5. So 1 is that. And let's express all in function of 11 and 13. So it's 11 minus 13 times 5 plus 11 times 5. So it's giving me 11 times 6, which is 66, minus 13 times 5, which is 65. 66 minus 65 is 1. It's correct. So I want the inverse of 11 modulus 13. So it is there. This is the inverse of 11 modulus 13. So I can say that what I was trying to solve was x. I come back from here. What is the inverse of 11? Is 6. Is congruent to 6 times 10 modulus 13. Okay, and what is 6 times 10? Is 60. So 60 modulus 13. And 60 is what modulus 13? So I can just ask my calculator. I can do it by myself, but I'm going to take advantage that we have Python here. And I'm going to ask Python to do that for me. So 16 modulus 13 is 8. So it's giving me 8 modulus 13, which is exactly the same result as we found previously. So it will be, the solution will be x belong to this set, no? Where we will have blah, 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 some value, we'll have 8, 8 minus 13 will be negative 5, negative 5 minus 13 will be negative 18, 8 plus 13 will be 21, 21 plus 13 will be 34. So where we have all this solution, no? That we should, I already make them disappear, and make them appear again. So we can see the negative 18, the negative 5, the 8, the 21, the 34. Okay, so that was another way to solve this. Okay, let's do this exercise, exercise 5. So here they say, calculate the modulus operation given below. Make a moderate usage of your calculator. The following property, this one, of the modulus operation should be helpful. So if we are doing A times B modulus n, we can do first A modulus n, we can do B modulus n, and then we multiply this result by this result modulus n, and it's exactly the same thing. So let's see how we use this property to compute, for example, that. Because we are going to manage very big numbers, and of course, we don't always have an infinite calculator. And if there is a way to do the operation with smaller number, even if we have an infinite calculator, is better to work with smaller number, because we will win in time. And since we need to save time, it's very important to use small numbers. So, okay, let's do that. So I have, let me put my pen again. I want to do 101 times 98, all modulus 17. So let me write, for example, modulus 17, like that. I'm going to write it. So I can do first 101 modulus 17 on one side. So this will give me what? So I can use my calculator here and ask Python. So 101 modulus 17 is 16. So instead of multiplying 101, I'm going to multiply 16, which is much smaller. On 88 modulus 17, let me ask Python that. 98 modulus 17 is 13. So I can use this number, or I can even use, for example, because we are in modulus 17, this will be congruent to also -1, isn't it? Because when we are modulus 17, I can add 17 as many times as I want, or I can subtract 17 as many times as I want. So 16 minus 17 is -1. And for example, here, I can subtract 17. So 13 minus 17 will be -4. So you see, instead of multiplying 16 by 13, I'm going to multiply -1 by -4, which is 4. So what can I say? That the result of all that will be 4. And that's it. You see, I didn't do a complicated multiplication like 101 times 98. I didn't even do 16 times 13. I do -1 by -4. And of course, I can ask Python to verify that, no? So I can type 101 times 98 modulus 17, and it say 4. So we made very moderate usage of the calculator just to compute that. And to tell you the truth, we didn't even have to do it. We'll have spent some time to realize that it was 16, but we could have done it. Okay, the second exercise is 7 to the power of 5 modulus 15. Okay, so I want to do 7 to the power of 5, and I want to compute it modulus 15, no? Modulus 15. So what do you think we are going to do there? I'm going to see the power of 7 modulus 15. So let's start with 7 to the power of 0. 7 to the power of 0 will be 1 modulus 15, no? Let's try 7 to the power of 1. 7 to the power of 1 will be 7 modulus 15. Let's try 7 squared. 7 squared will be 49. And 49 modulus 15 will be what? So 45, 49 minus 45 is 4, isn't it? So it will be 4 modulus 15, isn't it? Okay, now that I have that, I can do 7 to the power of 4. 7 to the power of 4 is the square of this. It will be 4 times 4. It will be 16 to the power 16 modulus 5. And 16 is just 1. Modulus 15. No? 4 times 4 is 16. And 16 modulus 15 is 1. So what can I say now? That 7 to the 5 is the same as 7 to the 4 times 7 to the 1. So if I do that modulus 15, let's do it modulus 15. So 7 to the 4, I have it, it's 1. And 7 to the 1, I have it, it's 7. So it will be 1 times 7, which is 7 modulus 15. And I'm done. So I did not have to compute 7 times 7 times 7 times 7 times 7, as you can see. Of course, and do it, no? 7 to the power of 5. Not a big number, but it's for us, if we have to do that without a calculator, it will take some time. Modulus 15, it says 7. The result is 7. And this is exactly what we found. 7 to the power 5 modulus 15 is 7. Okay, let's do 12 to the 8 modulus 7. So 12 to the 8 modulus 7 is what it was? Yeah, 12 to the 8 modulus 7. So the same thing I'm going to do. I'm going to see the power of 12. So 12 to the power of 0 is 1. So it will be 1 modulus 7. So 12 to the 1 will be 12. And 12 modulus 7 will be what? Will be 5, isn't it? So 5 modulus 7. 12 square. So I can say it's 5 times 5. It will be 25. 25 modulus 7 will be what? So we have 21, which is 3 times 7. So from 21 to 25, we have 4, isn't it? Modulus 7. You understand what I'm doing here? Where I say it's 4? It should be 25. But 25 is 21, which is 3 times plus 4. And 21 is 3 times 7. So the 3 times 7, I can remove it because I am modulus 7 plus 4. So it's I just have 4 here. Then I need 12 to the power 4. So it will be this square, which is 16. And 16 modulus 7 is going to be 2. Because 16 is 14, 2 times 7, that will disappear, plus 2. And finally, what I need is 12 to the 8, which will be the square of 2. The square of 2 is 4 modulus 7. So the result is just 4. The result of that is just 4. It's congruent to 4, or it's equal to 4, I can say. So let's see with our calculator that it's true. So I'm going to see 12 to the 8. It's a much bigger number than the previous one. As you can see, still small for Python. Modulus 7, and it's a 4. Okay, let's do this one. 7,559 to the power of 11, modulus 63. So we need the power of 7,559. So I'm going to start 559 to the power of 0. It's 1. So it will be 1 modulus 63. Now let's do the power of 1. So the power of 1 will be this value, modulus 63. So let's ask Python what will be the result. So I'm going to put 7,559 modulus 63. It's 62. So I can put here 62, but what will be a better value than 62? Because then I will have to do 62 square to have 7,559 to the square. And 62 square is going to give me some work. So in place of 62, I can put -1. Because 62 minus 63 is -1. I have no problem to do -1 square. -1 square is 1. Now, if you put 62 square, it will also give you 1, but it will give you more work. For example, 62 times 62, we better use the calculator to do it, no? 62 times 62, modulus 63. It has to be 1. Here it is, and I found it very easily because I put -1 here. Look, I came back here. So there is, it will be cyclical. The next one will be what? -1, 1, -1, 1, -1, 1. So here, look, when we will do this, no, it will be 1 forever. So now it starts to be 1 all the time because 1 square will be 1. I need the power of 8 and up to the power of 8. So 1 square will be 1. And with that, I can compute what I need to compute. So look at how it was easy. The only complicated calculus was this one that I asked Python. But then I did all by myself. So we need to solve 7,559 to the power of 11 modulus 63. So it will be the same as what? 7,559. 11 is 8 plus 2 plus 1 modulus 63. So first I need 7,559 to the power of 8. We have it here. It's 1. Time 7,559 to the power of 2. We have it here. It's 1. So time 1. Time 7,559 to the power of 1. We have it here. It's -1. So time -1 modulus 63. So this will be -1. So I can say it's -1, or I can say it's 52 modulus 53. Of course, if I ask Python, Python will give me a positive number. So it will say is 52. So let's verify that. We have 7,559 to the power of 11, which is a big number. Look. Okay, so this big number, I'm going to do it modulus 53. And it has to be 62, as you can see, no? This is what we say. So you see, even if they are very big number, I never compute something that big. Never. I use property of the modulus to keep my calculus very small. You can do this one. Let's do exercise 7. ASCII is a standard way to represent character as numbers. You know the ASCII table. For example, a space is represented by 32 in decimal. A comma is represented by 44. A lowercase, a period is represented by 46. The capital letter are also represented by integer, and they give you the integer that represent each of the capital letter of the alphabet from A to Z. So in the first place, we have the first 13 letters and then the last 13 letters. And of course, this ASCII table is available even here. So for example, I can type here man ASCII, and it gives me the ASCII table, and I can verify, for example, some of the letters. So for example, they were saying that the comma is 32. So look at, no, they were saying that the comma is, the space is 32. So look at, 32 in decimal is the space, the right space. Okay? For example, the W is 87, the capital W. Let me go there. The capital W is 87. Okay, and if you Google that, you have ASCII table everywhere. So you remember I told you the story will always be between Bob and Alice. And Trudy is the one that wants to make damage to this relation. So the public key of Bob is this one. So remember that the public key is two integers. The public exponent and the modulus. So this modulus should be a product of two prime numbers, P and Q, where E is the public exponent and N is the modulus. Alice wants to send to Bob, want to send him a secret message. See you this Sunday. To do so, Alice replaces each letter of the ASCII code and obtain a list of integers. So this 85 is S. So we can check with the ASCII table, but I'm going to do something that is better. Python also know about the ASCII table. So to get the ASCII code of, for example, S, I can use the ORD function. So it's telling me the ASCII code of S is 83. Good. Then this is CU. So this 69 should be a E. So S, E, E, this is a space. You remember that the space is 32. So then we have after the space, you have U. So this is Y or U. Let's just verify them. Y, the ASCII code of Y is 89. Correct. It is there. After the space, we have 89. The ASCII code of O is 79. And the ASCII code of U is 85. Okay. So C space U space this THIS space, and then we have Sunday, SUNDAY. Okay, so this is the way that we represent see you this Sunday with numbers. So there is other way to get that. Now that you are doing the homework number 2, you should be familiar with the XXD command. The XXD command can give me that. So let me copy this text, see you this Sunday. And how can I ask with XXD to have those numbers? So I can echo without enter this and pass it to XXD. XXD by default will represent them in hexadecimal. So I can say, please group them by group of 1. So this is the S, the E, but in hexadecimal. I can also tell XXD, don't show them in hexadecimal, because they are here in decimal. But of course, this 53 is 83. So 5 times 16 is 80. 80 plus 3 is 83. 4 times 16 is 32. 32 plus, sorry, 4 times 16 is 64. 64 plus 5 is 69, no? Okay, for example, this 20 is 2 times 16 plus 0, which is 32, which is the space. So can ask XXD, how do I show them in decimal? Can be decimal, hexadecimal, octal. Let me see. Is there an easy option? I don't remember. Maybe OD decimal, hexadecimal. I think OD is easier for that. Okay. OD, I can say decimal integer dash E, which will be integer dash E1. Do we have dash E1? Let me see. If I pass it, OD dash E1 dash I, yeah, but they are, I need to say the length also. So there might be a format option if I remember correctly. Okay, T dash T dash T, yes. So dash T, so it's that be dash T I1 maybe. Dash T I1. Dash T. It is in hexadecimal here. If I do octal, it will be in octal. So D1, oh, D1. Control. I want to reduce the size of the window. Otherwise, let me see if I can do it like that. Still too big. Okay, so is it okay? We have 83, 69, 69, 32, 89, 79, 83, as you can see, no? So I have them. Okay, so to do so, Alice replaced each character by its ASCII code and obtained a list of integer. So she did that already. Then she encrypted one by one each integer using Bob public key. So this is the public key. Remember that we encrypt normally with the public key of the recipient. She is almost done. You are required to complete the encryption message. So she already showed that 83 will be 49. 69 will be 217. So they ask you to complete that. So let's help us and complete the message, the encrypted message. So for that, maybe we use Python. And we put, for example, that E, the public exponent, is 257. That N, the modulus, is 551. Okay, and we are going to do the first one. Verify that 83, when I encrypt 83 with this public key, I get 49. So what should I write here to verify it? Remember, when we encrypt, we do what? The clear text to the power of the public exponent, modulus, the modulus. 49. So 83 become 49. Let's do the second one. The second clear text is 69. 69 become 217. Let's do the next one. The next one is 69. It will be also 17. 217. So I can write here 17. Then we have 32. So the plain text is 32. The ciphertext will be 185. 185. Then we have 89. So the plain text is 89. The ciphertext will be 90. Okay, we are going to do that faster. You have any idea how can I do that faster? You can use a list. So look, I'm going to show something that is very powerful in Python. Let's say that I have this list. -7, 11, and 20. And I want the square of 8, the square of 7, the square of 8, the square of -7, the square of 11, and the square of 20. I want to have the same list, but with square. So look at the list, L. So there is a function that is called map. When you use the map function, you put first a function here, the function that you want to apply to each element on a list. So we need to define a function that do the square for us on the list. The list, we have L, that is a reference to the list. So we already have the list. So we need to define a function that do the square. So let's define a function that we call square. If you do the square of x, you need to return x times x, or x times 2. Okay? Okay, I define the square. So let's verify that it's do the square. Square of 7, 49, good. Square of -11, 121, good. So my square function work. Now I can do map. I'm going to pass my square function, and I'm going to pass the list. Okay, it's a map object. I want a list. Let me convert it to a list. L-E-S-T, sorry. Let's verify. 8 square is 64. 7 square is 49. 8 square is 64. -7 square is 49. 11 square is 121. And 20 square is 40. So what map do? It applied the function to all the elements and create a new list where instead of having the element, we have f of the element. Let's say that I want to compute for each element, I want to compute 2 times x plus 1. So here 2 times 8 will be 16, plus 1 will be 17. Here I want to replace this 7 by 15. 2 times 7 plus 1. Here, for example, this 11, I want to replace it by 23. And this 20, I want to replace it by 41. What should I do? If I want to replace each element x by 2 times x plus 1, I need to define a function first. So let's define a function. So let me define a function that I call f, for example, of x. It doesn't have to be f of x, it can be y if you want. So I want to return 2 times y plus 1. Define. So let's verify that our f work. F of 9, 2 times 9, 18 plus 1 should be 19. Good. F of negative, for example, 77. Well, let's do this one, it's here. So it will be 2 times -70 will be -140, 140 plus 1 will be -139. Okay, F work, and we still have our L. So now I'm going to say apply F to L. Map F, comma to L. It will be a map, so I better put list, convert it to a list. It's an object. And look, 2 times 8, which is 16, plus 1 is 17. Let's verify this 11. 2 times 11 is 22, plus 1 is 23. 2 times 20 is 40, 40 plus 1 is 41. So now, look at what I'm going to do. Instead of Alice did it by hand. I don't want to do it by hand. We started to do it by hand. I'm going to get this one. On this one, you remember we have it with the OD command. So let me put them here. Edit, paste. Okay, we have the list. Now I want to encrypt this list. What should I do? I need to define a function. And I say, what should we do to add each plain text to convert it in a ciphertext? So let me define a function that I'm going to call encrypt. So encrypt receives a plain text. And it returns the ciphertext. So what should I write here in return? How do we compute the ciphertext? Huh? Those are basic formula that I already told you. So it will be m to the power of e is 257 modulus n. N is 551. So this is encrypt. Let's verify that encrypt of some value here that we have. The first value, for example, is what? The first value is 83. So let's verify what is encrypt of 83 to see it did work. Let's verify encrypt of 69. It did work. Let's verify encrypt of 32. It did work. So my encrypt function is okay. So what should I do now to get this list that she has to fill? I'm going to use the map function. I'm going to pass the function encrypt on the list that we have. Remember, that will be a map. This will be an object. So I need a list at the end. I convert this map into a list. And look at 49, 217, 217, 185, 90, and I could have gone up to the end. Okay, so look at how I use the power of Python to make the exercise easy to me. Okay, so you already help her to fill that. We have the solution here. Okay, you have the whole solution here. This is the encrypted message that she has to send. So let's say, just after sending the first message to Bob, Alice sent a second encrypted message to him as specified below. So she also sent this message. We know that the first message that she sent to Bob was, see you this Sunday. So they are going to have a date, as you can see. And she sent another message to him. So you are asked to crack this message. So in other words, you are asked to help Trudy, which is a bad girl. So let's try to help Trudy. So how do I proceed here? What will be your idea to crack this message? What will be your first step? So what I encrypt with the public key of Bob, I need to decrypt it with the private key of Bob. So if she sent that to Bob, this message was encrypted with the public key of Bob. So first I need the private key of Bob. So I need to infer, because I know what is the public key, I need to infer the private key of Bob. And here we don't have any problem to find the private key of Bob. Why? Because the modulus is very small. Of course, in reality, you are not going to take a small number like that. Because if you take a small number like that, they will hack you. You are going to take a number with 1024 bits. or 2048 bits. This number is just 16 bits. 16 bits. Any machine crack that today. You even crack that without using a calculator. So we are going to crack that. We are going to go back to the private key. Remember, RSA, reverse Shamir-Adleman, this method is based on the fact that it's difficult to factorize the modulus, because the modulus is a product of two big prime numbers. Okay, they recommend today 1024 bits for people. Military application have to go to 2048, 4096 bits. Okay? Okay, so what will be my first step to find the private key? So let's write what we know. We know that the public key of Bob is 257,551. It's two integers. So we want to find the private key. So we need to do what? We need to factorize 551. And it will be two prime number. It will be the multiplication of two prime number. So, okay, let's ask Linux to do that. Please factorize 551. 19 times 29. As you can see, 19 is prime, 29 is prime. So it's a product of two prime numbers. So it's 19 times 29. This is the problem that we were able to factorize. You should not be able to factorize. That's why you have to use very big number. So I can use P as 19 or I can use P as 29. It doesn't matter, it will be the same thing. So let's compute. This is the modulus. Let's compute the totient. How do we compute the totient? P minus 1 times Q minus 1. So it will be, let's say that you take for P 19. So 19 minus 1 is 18. And let's say that you took for Q 29. 29 minus 1 is 28. So 18. Let me ask my computer to compute 18 times 28. 18 times 28 is 504. Okay, it's 504. So you need to resolve E, the public exponent, times D, I don't know D. The private exponent is congruent to 1 modulus phi. So what I know here, I know E is 257. I need D. If I have D, I have the private key of Bob. I know phi, we just compute phi. Phi is 504. So I need to resolve this equation, and we know that this equation has a solution. So to do that, what should I do? I need the inverse of 257 modulus 504. So we are going to express 504 in function of 257. So it's 257 times 1 plus here. So I'm sure I don't make any mistake. 504 minus 257 is 247 plus 247. So now we need to express 257 in function of 247. So 257 is equal to 247 times 1 plus 10. Now I need to express 247 in function of 10. 247 is equal to 10 times 24 plus 7, isn't it? Now I need to express 10 in function of 7. 10 is 7 times 1 plus 3. Now I need to express 7 in function of 3. 7 is 3 times 2 plus 1. Bingo, I reached the 1. I can go back. So I have to use each one of this line. So the first one, I use first this one. So 1 is 7 minus 3 times 2. Okay, let me write it here better. 1 is 7 minus 3 times 2. So I already used this one. Now let's use this one. I'm going to take this 3 and replace this 3 here. So it will say that 1 is 7 minus 3. So 10 minus 7 times 2. And I'm going to express everything in function of 7 and 10. So it will give me 7 minus 10 times 2 plus 7 times 2. So in function of 7, it will be 7 times 3. And in function of 10, it will be 10 times 2. 7 times 3 is 21. 21 minus 20 is 1. It's correct. So I already took advantage of this one. Now I have to take advantage of this one and replace the 7. So 7 is 247 minus 10 times 24. So let's replace here the 7 by 247 minus 10 times 24 times 3 minus 10 times 2. So let me verify that I did it correctly. 247 minus 10 times 24, correct. So if I express everything in function of 247 and 10, I will have 247 times 3 minus 10 times, okay, 24 times 3 is what? 72. Okay, minus 10 times 2. So in function of 247, I will have 247 times 3. And in function of 10, I will have 10 times 74. Let me just verify it to be sure that we don't make any mistake up to this point, so we can go forward very sure of what we are doing. So show me the result of computing 247 times 3 minus 10 times, should be 1. Good, we have not made any mistake. So now I'm going to replace. I'm going to take this one and I replace 10 by 257 minus 247. So let's replace 10 by 257 minus 247 times 74. So it's giving me in function, I have to express everything in function of 247 and 257. So minus 257 times 74 plus 247 times 74. So in function of 247, 3 plus 74 will be 77 minus 257 times 74. Okay, and I need to take advantage of the last one. So I just took advantage of this one. I need to take advantage that 247 is 504 minus 257. So the 247 that is here, I'm going to put 504 minus 257, no? Let me see. So it's 504 minus 257, correct. So minus 257 times 77 minus 257 times 74. So I'm going to express everything in function of this should be 1 in function of 504 and 257. So this is 504 times 77 minus 257 times 77 minus 257 times 74. So give me 504 times 77 minus 257 times 77 plus 74 will be what? Okay, I don't want to. 77 plus 74 will be 151. So 151. Let's just verify that this is correct. If this is correct, we have the inverse. So compute 504 times 77 minus 257 times 151, 1, as you can see, bingo. So we have modulus 504, and we want to find the inverse of 257. So who is the inverse of 257? So since we have modulus 504, this can go. This can disappear. So the inverse of 257 will be negative 151. Let me write. The inverse of 257 will be negative 151. On negative 151, modulus 504, I can add 504. So to put it as a positive number. So let me do that. So negative 151 plus 504 is 353. So it's 353 modulus 504. So the inverse on the D that I'm looking for is 353. So the private key, let me write both. We know that the public key of Bob is 257 551, if I remember correctly, no? Verify that. 257 551. And the private key of Bob, only Bob have this key, is 353 551. So let's go back to Python. I went out, so let me come back to Python 3. And I want to define the encryption function. So the encryption function will be what? Return. So the plain text to the power of E, which is 257, the public exponent. Modulus n, modulus 551. Modulus 551. And the decrypt function will receive a ciphertext and return what? So it's the ciphertext power D, which is 353, modulus 551, modulus n. So now that I've done that, let's verify that everything works. So for example, look, I'm going to say encrypt 83. I should have 49. And now I'm going to say decrypt 49. I should come back to 83. Okay, let's do decrypt 217. Decrypt 217. I came back to 69. Decrypt 185. Decrypt 185. I come back to 32. So what can I do now that I find the decrypt function? I decrypt one by one. So let's decrypt 491. Message starts with 66. So 66 is a letter. So of course I can look at the ASCII table to know what is 66. So look at man, ASCII, and 66 is there. It's a B. Okay. But we have Python. Let's ask Python to do that for us. So what should I do here? Apply the CHR function, which will convert an ASCII code to the character B. So it starts with B. Then we have 217 PE. Then we have 185 space. So it starts with B space. Then we have 205. There is a O. Then we have 488. There is an N. Then we have 185 will be a space again. So it starts with B space on space. This is what we know already. So then we have 221. 221, there is a T. Then we have 213. There is an I. Then we have 515. 514. There is an M. Then we have 217. There is an E. And the message is that. So what was the second message that Ali sent to Bob? What is the second message? Huh? Be on time. Okay? So she first sent a message that was saying, see you this Sunday. And then she sent a second message, be on time. So Trudy was able to decrypt. She's going to appear in the park also on damage day date. So you see how easy it is. It is based on that. Which means that if you look at a certificate have the modulus inside, and we make that public. Which means that if somebody is able to factorize and find P and Q, this person will have the private key. And with the private key, this person will be able to decrypt. So our security is based on the fact that it's very difficult to factorize the product of two big integers. It's very, very difficult. And you can see, we can take a certificate and look at what integer is inside, what product of two integers is inside. We will see a product of two integers. We'll see the result, but we will not be able to go back and to find P and Q, because of course it will be two big integer. By the way, what could we have done here instead of doing one by one? I could have done the same thing that we did previously. I define a list, L. I put all what I've captured in the medium in L. So L have the ciphertext that Alice is sending to Bob. And what are we going to do? Use the map function. We are to pass the decrypt on L and convert this to a list. Look at what we get. So instead of passing decrypt, I can have do what? I can define another function like Like what? That give me the character directly. The character once it is decrypted, no? We see decrypt. Oh, yeah, decrypt on the list. I'm kind of surprised of this big number. Is the list was correct? List. Oh, the list was not correct. I was saying I'm surprised of this big number. I copy that. Let's see, edit copy. Edit paste. Okay. So let me see the list. The list is okay. And let's call this. Okay. So look, this is B space on space time. But what can you do here? I'm going to map function. What function should I put? CHR. I need to create a list with that. Map CHR or list. Look at B space on time. Now I want to join them. You remember Python? Join all this. Be on time. You see the power of Python? You don't have to suffer. Just exploit all the programming language feature. And you give me the list and look at what I've done. One command. Give me the clear text without any problem, without I have to pass from ASCII code to character. They are already in character. They are already together. They are not even separated because I joined them. Okay? Okay, so in the real world, Bob has his pair of key, but Alice also have a pair of key. So if Bob wants to answer, I will be on time, don't worry. It have to use what? Let's say that Bob now wants to answer to Alice and say, I will be on time. To encrypt I will be on time, you have to use what? Which key? Huh? Which key? The public key of Alice. If I'm going to send a message to Alice, I need to encrypt it with the public key of Alice. Remember that Alice make the public key available to everybody. So if I want to send us a message to Alice, I have the public key of Alice because she made it available to everybody. I encrypt with the public key of Alice. The only person in the world that will be able to decrypt what I encrypt with the public key of Alice is the person that have the private key of Alice. So I send that on the medium that is unsecure. It's not a problem because the only person that have the private key of Alice is Alice. So when Alice receives the ciphertext, she will use her private key to get back to the clear text. So everybody have a pair of key. Everybody publish its own public key. Let's say that you want to send me something, you need my public key. And of course, I publish my public key, so you have my public key. You encrypt with my public key. You send it in an insecure medium. It's not a problem. I receive it, I use my private key, and I decrypt. Now I want to reply to you. I use your public key. If I want to reply to John, John sent me his public key, or I found the public key of John in the web page of John. So I use the public key of John. And I encrypt with the public key of John. John received my ciphertext. John used its private key to get back to the plain text. Now with that, we also do signature. A signature is a way to say, I send this message and this is mine. I sign it. For example, you are sure that it was sent by myself. So how can I sign? Let's say that I have a text and I want to send it. And you want to be sure it was sent by myself. So what I will do is I will take a summary of the message with a hash function. So we have several hash functions. MD5, SHA-1, SHA-256. We have a lot. So I take a hash, which is a fingerprint of the message that I want to send you. And I encrypt this fingerprint with my private key. I send the message with the signature. The signature is the encryption of the hash with my private key. When you receive the message, how do you know for sure I send the message and it is signed by me? So you take the original message, you compute the hash. You don't have problem to compute the hash. Then you have the hash that I sent, but the hash was encrypted with my private key. Since you have my public key, you decrypt the hash with my public key. And you compare the hash that you calculated with the hash that you decrypt. If both are the same, the message was sent by me. Because the only person that can sign this message is me, because I have the private key. Is me Eric, because I have the private key of Eric. So you sign also. So you don't only encrypt. So let's say that now I want to send you a message. I want to sign it, and I want the message to be encrypted. What should I do? So I have the clear text message first. I compute, for example, the MD5, which is the digit, which is a summary, a digital summary of the message that I want to send you. I encrypt it with my private key. Both of them, I concatenate them. I use your public key to encrypt the whole, and I send it to you. You have your private key. Since I encrypt the whole message, which is the plain text and the signature with your public key, you can decrypt and separate the plain text and the signature. So you have the plain text. Now you need to be sure it was sent by me. So what do? You verify the signature. So you compute the MD5 of the plain text that you receive. And there is another MD5 that is encrypted, that was sent in the message. It was encrypted with my private key. since you have my public key, you decrypt this digest, this message summary, and you compare the two digests. If they are equal, you are sure that I sent it. Okay? This is a way of creating what we call no repudiation. Which means that you send a message and after say, no, I never sent that. For example, you ask the bank, transfer that much money from here to here. And then you go to the bank, you say, I never did that. I never told you to do that. So the bank can show, yeah, you did, because you signed this message. And this is legal in the majority of the country, that you sign digitally. And you cannot say it's not you. It's like you sign by hand. It's already considered that you sign by hand. Because you are supposed to be the only person that have your private key. So nobody can sign for you because they don't have your private key. So it's why it's very important to keep in secret your private key. So as you can see, with this algorithm from RSA, Ravir, Rivesh, Shamir, and Adelman, you can do both. You can encrypt and you can sign. So the public cryptography is considered very slow. And the private cryptography is considered very fast comparing to the public cryptography. So even if we can use the public cryptography to do everything, for example, to encrypt a long message that I want to send, we usually don't do that. And we use the public cryptography only at the beginning of the session to agree a private key, a key for the session. So one of the two parties that want to communicate generate a private key. For example, let's say that we are going to use triple DES. One of the two parties generate a private key and send it to the other party using public cryptography, which is slow. People can copy the communication they don't understand. They cannot see the private key. When we agree about a private key, we don't use public cryptography anymore because it's too slow. We use triple DES, which is faster, for example. Or we use Blowfish or Twofish or AES or any encryption algorithm that is symmetric. So this is what you do in the internet and you don't know that you are doing that. But when you connect to a bank, all this process is done. Okay. Do you have any question? I think we can stop here for today. We will continue doing exercises. It's too long to start this one or this one. We will continue to do exercises on Thursday. So keep looking at the exercises and don't forget to work on the assignment. And of course, I need a very high quality report. Okay, I don't need a report. I really need a report that shows that you present well your data, you know what you are doing. Okay? Okay, I see you in 2 days.